Okay, so I told you guys last week that redox reactions are one of the places that redox reactions are important and are used, that are taking place all the time, are in batteries, right? Because when we talked about redox reactions, what's happening in redox reactions? We're tracking the number of what, as we write the oxidation states, the number of electrons, right? And what are what is so as we're tracking the change in the electrons on the reactant side versus the product side, right? So if the electrons are moving as we go from one side to the other, well, electricity by definition is the movement of electrons. Okay, and so we can actually produce electricity through these redox reactions, and that's kind of the science behind batteries. And so we have something that we call a galvanic cell. And a galvanic cell is a system that uses a redox reaction, bless you, uses a redox reaction to produce electrical energy. Because electricity is the flow of electrons, and that's exactly what we have in, bless you, have in redox reactions. We have the movement of electrons there. So if you look on page 368 in your book, you'll have a diagram of a galvanic cell, and it's got particular elements labeled here. So in this particular galvanic cell, you've got these two containers on each side. Make that a little bit wider. I don't know that I made it wider like I wanted to. Let me try this one more time. So we'll have room for our electrode in there. So you've got an electrode in this side. It's just a solid piece of metal. You've got an electrode on this side, which is a solid piece of metal. So we're going to kind of color those in. And then a wire that connects those two electrodes together. Our electrons are going to flow in this direction. So that's electron flow. And then we've got a liquid in here on both sides. So some sort of solution down the bottom here. And we've got what we refer to as a salt bridge. It goes from one container to the other as well. And we label this side with a negative. This is an electrode right here. This is an electrode right here. This is the positive side. We call this the anode. And we call this the cathode. Now, you're going to have problems where I'm going to ask you to draw the galvanic cell that's represented by a particular reaction, okay? And so I wanted to draw just this portion of it first because this piece is going to be the same for every one of your diagrams that you draw. All right, so you need to memorize the various parts of the galvanic cell here. By definition, the anode is the negative electrode. And so you'll see this is the anode on this side. You see the negative side there. It's the negative electrode in a galvanic cell or battery. And so this is where electrons come from. In other words, this is the side that's producing the electrons or losing electrons. So if this is the side that's losing the electrons, then is oxidation or reduction happening on the left side? Oxidation, right? It's Leo. Remember Leo, the lion, says what?
Leo says Gur.
Leo says Gur, right? So loses electrons, that's oxidation. Gains electrons, that's reduction. So where electrons come from, so let me finish the thought here. Oxidation happens here. All right? Leo, that's how we remember that. And so the cathode is the opposite of that. Cathode, in contrast to the anode, the cathode is the positive electrode. All right, where the electrons travel to. That's the side that electrons go to. So in other words, i.e. where reduction takes place. And we remember that by Gur. Gains electrons, then reduction is taking place over here. So this, if I say draw the galvanic cell, every time these are the pieces that need to be in it. So I would start with this drawing here. It doesn't have to be as elaborate. I don't care if you color these things in, right? If you do any kind of shading there to show that there's a liquid down in there or whatever. I'm not so concerned about that. It can be very boxy, right? Something like this, where you've got a container over here. Just show that we've got some liquid in there, and show the salt bridge. And so label all those things. Label the flow of the electrons. Label this side as negative, this side as positive. Label that as an electrode, right? I just want those basic pieces in there. Then the other thing you're going to have to give me is you're going to have to tell me if I give you a reaction, like this reaction here, 2Al solid plus 3Cu2 plus aqueous, 3Cu solid plus 2Al 3 plus aqueous. One side of your galvanic cell is going to have aluminum as well as the aluminum ions. And the other side of the galvanic cell is going to have the solid copper and the copper ions. And the way that you determine which one goes where is by looking at the oxidation states to figure out which one is oxidized and which one's reduced. Okay? So let's consider the oxidation states of this reaction right here. Al is going to have what oxidation state? Based on our rules. 0. It's going to have 0, right? This one's actually really simple. What's the oxidation state of Cu2 plus?
2.
The Cu is 2 plus. Here the Cu is 0. Here the aluminum is 3 plus, right? So the aluminum, as it goes from the product side to the reactant side, becomes more positive. So it gained or lost electrons?
Lost.
It lost electrons. Leo, so it was oxidized, right? Al is oxidized. Cu, however, became more negative. This number got more negative. So it gained electrons. Gur, gained electrons, is means reduced. So Cu is reduced. All right? So the one that's reduced, the one that gained electrons, is going to be on the side that the electrons flow to. Right? You guys see that? So Cu is what's got to be represented over here. Well, if you've got a solid, then make the solid your electrode. Okay? So in the case of Cu, on the product side, we have a Cu solid, so we say this is a Cu electrode. It's an electrode made out of copper, solid copper. And then right here, in this, we have a Cu2 plus solution. Right? That's the aqueous solution that the copper ions are in. And then we've got an electron made of solid copper. And we do the same thing on the other side where the oxidation takes place, the one that's losing electrons. We've got solid Al, so we've got an aluminum electrode, and we've got a solution of Al3 plus. All right? So this should be really easy for you as long as you memorize what the pieces are of the galvanic cell, right? Just draw all of those basic pieces, and then it's just simply a matter of figuring out which one was oxidized and which one's reduced. And so you know which one to put on each side. If it's aqueous, then it's going to be down here in the solution. Now, if the way this equation had worked out is that the copper over here was actually a copper in an aqueous solution rather than a solid, then we would just put it down here. We would say this is a Cu2 plus and Cu solution. We'd say that they both were in the solution, okay? And then the type of the metal that the solid electrode is made from wouldn't matter. But if you've got one that's a solid, then go ahead and label the electrode as that solid. Does that make sense to everybody? Anything confusing about that? I want you to understand why I put Al here and not Al3 plus, because Al was the solid. So that's what the electrode is. And this is the solution, Al3 plus. Same thing on this side. Cu2 plus solution, Cu, solid Cu is the electrode. Everybody clear on how to decide which side each one goes on? All right. Okay, well, let's do an example and see if you really are clear. All right. Oh, by the way, let me just real quick mention this. This is just a wire here, right? So this is where the electron flow takes place. The flow of electrons is what electricity is. And so because we're getting an electron flow here, it means that we can power something with that, right? It produces electricity. Also, what's the purpose of the salt bridge? Remember what we refer to as a salt in our acid and base reactions? You remember that? We'd have those acid and base reactions where you had an ionic base that would produce water and what?
NaCl?
Could be NaCl, depending on what was in it, but a salt. And we were using salt as a generic term in those reactions to mean that it was what type of compound?
Ionic.
It was an ionic compound, right? So a salt is just an ionic compound, and what it does for us here is because it can split up into positive and negative ions, then it can keep this solution over here balanced, electrically balanced, so that it won't get too negative or too positive. So that's the purpose of the salt bridge, because if it gets if the anode side becomes too positively charged, then no more electrons will flow over there. So it just maintains the balance. That's the purpose of the electrical balance. That's the purpose of the salt bridge. All right. So if I give you a redox reaction like this one here, you should be able to draw and label the galvanic cell that reaction represents. And so let's do one of those. And we've got an example on page number 372. Yep. So here, the reaction for this galvanic cell is Cu plus 2Ag. The Cu is solid, the Ag is aqueous. Cu2 plus aqueous plus 2Ag, running out of room here, which is a solid. So that's our reaction. You can use our same exact drawing, but we're just going to remove these pieces here, right? Because that's going to be different for this reaction. So what do we need to do now that we have our chemical reaction, our redox reaction? First step is to find the oxidation states, right? So we got a 0, we got a 1 plus, we got a 2 plus, and we got a 0. Everybody follow that? This was really simple and straightforward. If it doesn't have a charge listed, it's 0. Since it's just a single element all by itself, if it does have a charge, then that is the oxidation state, right? So Cu becomes more positive, so Cu is what? Becomes more positive, that means it lost electrons.
Oxidized.
Leo, lost electrons oxidized. So that's oxidized. And then the Ag becomes more negative, so the Ag must have been reduced. So if it was reduced, it gained electrons, so the electrons are flowing to that side. So this is the side that gains electrons. The Ag, wait a minute, yeah, Ag in this equation. So we've got solid Ag over here, so we're going to label this electrode as Ag, and we're going to say this is an Ag plus solution. And we're going to say that this is a copper electrode on this side, because that's the one that was reduced, and that it's a Cu2 plus solution. Everybody see how easy that was? Nothing to it as long as you recognize the basic diagram and then you remember which way the electrons are flowing. Yes?
And you wouldn't put the like the number that's in front of the element, just to be clear. For example,
No.
2 Ag. You wouldn't.
Yeah, you wouldn't put the 2 there, right? You just put in just whatever the substance is, whatever the compound is. I wouldn't count it off if you put the 2 Ag on there, because I just want you to recognize that this solution is made up of the silver ions. But yeah, you don't need to put that because it's really, remember this represents moles, and this may not be 2 moles of solution in here. It's just, it's probably more than that, right? It's just a solution made up of silver ions. Okay, any questions about that one before we do the next one? Let's do one more. And the next equation, a little bit different than the last one. We've got 2Hg, 2 plus aqueous, plus zinc, which is solid. And it produces Hg2, that's 2 plus aqueous, plus zinc, 2 plus aqueous. So here, we've got only one solid in this reaction, and we've got everything else is aqueous. So just to, again, show you how, well, first let's do the oxidation states. This is a 2 plus, this is a 0, this is a 2 plus, this is a 2 plus. Actually, this is not a 2 plus, sorry. This is a 1 plus, because the total charge is 2 plus. Yes?
How come the aqueous and solid states switch in the second half of the problem?
Why it switches is not really so much the question. It's just I want you to note that because it's going to affect how you label your galvanic cell. Okay, so the fact that you notice that is important, and that we're going to show you when we label the galvanic cell where you put that. Okay, so good question. We'll get to that in just a second. Does everybody understand why this is 1 plus?
No.
Okay, the reason it's 1 plus is because this is Hg2, right? And so if the overall charge of the ion is 2 plus, remember when we write down the oxidation states, we're just looking at Hg, a single atom of Hg. So if there are 2 of those and the total charge is 2 plus, then a single Hg's got to be just 1 plus. Does that make sense? So that's why that one's 1 plus. So now we can see, because we would have had a problem if this had been 2 plus, because when you have reduction, you always have oxidation as well, right? And vice versa. And Hg wouldn't have changed, and so zinc became more positive, so it lost electrons, so it was oxidized. but we wouldn't have had something reduced. So I made a mistake of that in the first class. I'm like, wait a minute, this isn't working out. So the Hg becomes more negative. It goes down in its oxidation state from 2 plus to 1 plus. So since it became more negative, it gained electrons, so it was reduced. And then the zinc was oxidized. All right. So I'm gonna draw the galvanic cell over here real quick. A very simple version of it, and just show you this is all that you have to do on your on a quiz or an exam. Draw your electrodes. Draw your wire between your electrodes. Draw your salt bridge. Identify that there's some liquid in here, right? Label that as an electrode. Label this is the side that's producing the electrons, so they're flowing that way, so flow of electrons. This is my salt bridge. All right. This is my negative, this is the positive side. And think about, when you think about this negative and positive here, this is positive because it's attracting the electrons, right? The electrons are flowing over there to that, so you got a positive charge that's attracting those. Label this as my anode. Whoops. Label that as my cathode. So that's the simple drawing that I expect you to draw, right? It doesn't have to be very pretty. And then I just need you to identify which one is on each side. So the one that the electrons are flowing towards, that's gaining electrons, GR. So that's the one that's reduced. So we've got Hg on this side. But notice in this one here, Hg is aqueous on both sides. So this is what you do. You label this as the electrode. And you say that this is an Hg2 plus and Hg2 2 plus solution. So if both of them say that they're aqueous, then both of them are in this solution down here. Okay? And in that scenario, it doesn't matter what the electrode's made out of. It can be any metal. In a battery that they're going to manufacture, it's going to be the cheapest metal, right? So this can be any metal here, but this one on this side, because this is the side that the oxidation takes place on, we do have solid zinc. So we label this electrode as a zinc electrode. Okay, it's the solid. And then this is a, you could write in here if you wanted to, Zn2 plus solution. All right, so you don't have to get too artsy on it, especially when you're taking a quiz and you're limited on your time, right? So as basic as possible, but these are all the pieces that I want you to have. So I want to see your electrodes labeled. I want to see the negative and the positive sign here. I want to see the flow of electrons identified. I want to see this identified as the salt bridge at the bottom. I want to know which one's the anode and the cathode. So those are all pieces that every drawing is going to have, and then you're just going to be plugging in the appropriate compounds for those pieces. Is that clear to everybody? So like on a test, right, there's like 1, 2, 3, 4, 5, 6, label the electrons, the electrodes 7, 8, the correct flow 9, this is your, label these properly. So we've got like 10 items here. This is like a 10-point problem on a test, right? So whether or not you have each of those things correct is how I'll end up giving you partial credit on that one. All right, any questions about drawing a galvanic cell? Yes?
So for that example, there just wouldn't be an electrode labeled on the cathode side?
That's right. It can be any metal. It doesn't have to be, what's Hg? Mercury?
Yeah.
It doesn't have to be a solid piece of mercury, right? They can use any metal for that. It's just that we've got to have the mercury ions available down here in the solution. And so what would happen in that case is that this electrode here, we're going to learn about something. The very last thing we're going to look at, and we're actually going to do an experiment with, is what's called electroplating. And it's it's how, like, if you have a piece of jewelry that's gold plated or silver plated or whatever, it's what they use. They use a redox reaction to do that, right? So if you were to pull this metal out after these reactions had taken place, you would see like solid mercury accumulated on it. So it would plate whatever that metal is there. All right. Okay, let's move on to our rest of our topics. I'm not sure, but your quiz next week may just be I give you an equation and you draw the galvanic cell associated with it. So make sure you know how to do that. Like I said, I haven't looked at the quiz, but that seems very familiar. I know it's definitely going to be on the test. I can't remember if it's going to be on the quiz or not. All right, let's talk about balancing redox reactions. Now, in the past, when we've balanced equations, all we've had to count up is what? Make sure we've got the same number of what on the left side compared to the right? Same number of atoms, right? That's all we've cared about in the past. Well, now that we know about oxidation states and we know that redox reactions exist, and we recognize that that's a transfer of electrons, matter always has to be conserved, right? It can't be created or destroyed. And so whatever electrons you have on the left side of the equation have to match the number of electrons on the right side of the equation. So as those electrons are flowing back and forth, since we're tracking those based on the oxidation state, then when you add up your oxidation states for each side, they should equal the same. Okay, so we got to balance. So balancing redox reactions is a little more complicated than what we've done in the past. So for a chemical equation to be balanced, the total charge on each side of the equation must be the same. Matter can't be destroyed, so we need the same number of electrons on each side of the equation. So I'm going to write down a reaction here. You're finishing up copying that. So what we've learned previously, if I were to give you that reaction there, and I would say balance this equation, you would say it's already balanced, right? Because we got 1 Ag here, we got 1 Ag there. We got 1 Mg here, we got 1 Mg there. So when we count up the atoms are balanced, right? But when we look at the oxidation states, this has an oxidation state of 1 plus, this has an oxidation state of 0, this has an oxidation state of 0, this has an oxidation state of 2 plus. So when we add up the total on that, just like you were talking about earlier, Jerry, with the 2 and how it applied to the OH, and we were adding up the total charge, right? If we add up the total charge of this system here, we've got 1 plus, right? 1 plus plus 0 is 1 plus, and the total here is 2 plus. So this equation is actually not balanced because the charges don't match on each side when we add these together. So we're going to do the same thing that we've done in the past. We can only, when we balance an equation, we can only mess with the big stoichiometric coefficients in the front, right? We can't touch little numbers down here or anything like that. We can only adjust the big number in the front. So we're going to play around with the numbers in the front to make this balance out. And what we need on this one here is we need this side to be 1. We need another 1 plus, right? We need to be this one more positive by 1. Let me say it that way. So this one's a simple one. The only thing we have to do here is put a 2 in front of that, right? So now we've got 2 1 pluses. And so that's going to give us a total of 2 plus there and a total of 2 plus here. And it balances on that side, but now we have another problem because we put a 2 there. What's our other problem?
Oh, it's not balanced with the atoms.
By the atoms, right? What we've learned in the past. So we got to be balanced that way as well. So in order to do that, we put a 2 there. And since this one's 0, 2 times 0 is still 0. So we're actually still balanced electrically as well. Does everybody see that? Now I want to point out something. If I asked you what the oxidation state of Ag was on this side, you would not write down 2 plus. You would still write down 1 plus. Because remember, when I ask you the oxidation state, I'm asking the oxidation state for a single atom in that compound, right? I'm just saying the total oxidation state, since I've got 2 of these atoms now, is 2 plus. So I take the 2 into account when I'm looking at the total charge on this side of the equation, right? But if I'm looking at just the oxidation state for silver in that compound, it's still going to be 1 plus. Does that make sense to everybody? All right, I don't want you to, I mean, I'm never going to give you that if like I did before. Well, no, I will. I'll give you an equation like this and I'll say, is it oxidized or reduced? And if you're checking to see if it's oxidized or reduced, you're still going to write it like that, 1 plus, okay? All right, so I think we do an example next, actually make sure that we can do this with some other problems. Page 375, example 12.5, yeah. So let's balance some of these redox reactions. And this particular redox reaction is Cu solid plus Fe3 plus aqueous, Cu2 plus aqueous, plus Fe2 plus aqueous. All right, so we, again, this one's balanced as far as atoms are concerned, but let's write down the oxidation state. And we see when we do that, that the total charge on this side is 3 plus, right? And the total charge on this side is 4 plus. So we're clearly not balanced. So what, if I'm looking at this, what element am I going to focus on as far as adjusting the number in the front first, do you think? Is it going to be the copper or the iron? And why? Let's just think about what we've got to do. We can't mess with any of the numbers in the front and make anything more negative, right? Everything's positively charged or 0. So the only thing we can do is we can make something more positive by putting a number in the front. And so what we need to do is we need to bring this side up. Does everybody see that? To try to match the 4 over here, right? So if we think about bringing this side up, is adjusting the number in front of the copper going to do anything? No, because it's still going to be 0 no matter what. This side's not going to become more positive when I do that. So this is the one that I need to mess with to make that side more positive, right? So if I do this now, instead of 3 plus, the total on that's going to be 6 plus. And so our total over here is going to be 6 plus. But if I bring this up to be 2 Fe3 plus, I'm going to have, in order to balance the atoms, I'm going to have to put a 2 there, right? So let's check our oxidation states again now that I've done that. This remains 2 plus. Now we've got 2 times 2 plus for a total of 4 plus here, and we've got a total of 6 plus. So now we're balanced both at the atomic level, as far as atoms go, and we're balanced as far as the charges go. Does everybody see that? Does everybody see how I made those decisions, which element to mess with? You could have played around with the Cu, but if you'd have started messing with the numbers there, I think you'd have realized pretty quickly it's like this is going nowhere, right? If you adjust this number over here, this just gets more and more positive, and you're adjusting this number here and it's not doing anything, right? So you're never going to reach your goal by doing that. And we needed to make this side more positive. Okay, let's do another example that's a little more complicated. And this one is that I2 aqueous form. So they don't give us the whole equation this time. What they say is that we have a redox reaction in which I2 is reduced to 2I negative, all right, in aqueous form, while Fe, iron, in solid form, in its solid phase, is oxidized to Fe3 plus. Right, so you have to, it's kind of like a word problem. They wrote everything down for us in words, and we have to translate that to the chemical equation. And they say, what is the balanced chemical equation? All right, so we start writing down our oxidation states because we see immediately that the atoms are balanced. But let's check the oxidation states now. So 0, 0. This is going to be 1 minus, but we've got 2 of those, so 2 minus, and this is going to be 3 plus. Right? Your brow wrinkled. What's confusing? Anything? No? Okay. I just want to make sure, does everybody understand why I did 2 minus here? Because I'm checking the overall charge, right? I'm not looking at the oxidation state just of the I. If I was just going to write the oxidation state of the I would say 1 minus. But because I've got to check the total charge of the system, the total on this is 2 minus. So 2 minus plus 3 is 1 positive, positive 1, right? But over here, we've got a total of 0. So we're off by, we need to either make this more positive because we want it to be positive 1, or we're going to have to bring the positive 1 over here down to 0. So here's my question. Can I make this side more positive? Can I mess with the coefficients in the front and make it more positive? No matter what coefficient I put in the front, this side's never going to be anything but 0, right? Does everybody see that? So I'm not going to mess with this side to start with. This is the side that I need to focus on. And so basically what I need to happen here, since we're adding these two together and one's negative and one's positive, I need these numbers to be the same. You guys see that? Mm-hmm. So let's play around with that. Let's see what we can do there. So if this is going to be 3 plus, no matter what, I can play around with the stoichiometric coefficients, but this has a 2 in front of it, so what if I made this a 3 instead of a 2? What if I made it 3? Would I be balanced over there? I would, right? That would work. Because now I've got 3 negative here and I've got 3 positive here, which adds up to 0. But can I balance my I's if I make that a 3? I can't, right? Because I've got a 2, I2 over here. Now there's a trick that we learned, and that is that I can do this. I can make this 3 halves. And if I make it 3 halves times 2, 3 halves times 2 equals 3, right? So that'll give me a total of 3, but we can't have fractions in our stoichiometric coefficients. So the way that we get rid of that is we multiply the whole thing by 2. And so now if I multiply everything through by 2, then I got 3i2 aqueous plus 2fe solid. 2 times 3 is 6i minus aqueous plus 2 times 1 there, 2fe, 3 plus aqueous. And so now if we check everything again, we got a 0 here, we got a 0 here, we got a 6 minus here, and we got a 6 plus here, which adds up to 0. So now we've got a total of 0 on both sides. All right? Now, if the fraction thing is confusing to you, maybe you didn't really get it the first time that we did it, right? All those months back when we went over that, you're not going to have to play around with the coefficients too much. You could again just kind of note the fact that this had a 2 in front of it here, and it was like that to start with. This had a 2 in front of it, so you could start by saying, let's just play around with this and put a 2 here, and rebalance everything and see what happens. And so if you did that, you would have this, and you would have 2 negative, and you'd have 6 plus. And then you could recognize, well, if I change that from if I want to make this 6 negative, then I could put a 6 in front of this, right? And now I've got a 6 negative, so we've got a total of 0 over here, but I've got to balance my I's, and I can put a 3 in front of that and make that, that's still 0. So you could go about it that way, whatever makes the most sense to you, as long as you come up with these numbers in the front. Yes.
And so if there's already a number in the front of an element, you can just get rid of that and change it?
You can when you're doing when you're doing these redox reactions and you're trying to balance out the charges. You can start playing around. You can do those numbers differently than you were doing before. Really, we didn't change it. Let's see, it had a 2 in front of it. Well, we definitely changed the numbers in front of the other ones. So remember, these really have numbers there, even though we're not writing it down. There's really a 1 there. So every time we mess with these numbers, we're changing the numbers, right? So yeah, you can totally change that number. I was going to try to show you how we were sort of multiplying through, but that doesn't even work out without messing with these other numbers first. So yeah, just replace that with something else if it's not working. Okay? Just can't do halves like we did a minute ago. If you get a half in there, if you're like, this totally balances if I can use a fourth or a half, if you stick it in there, you just got to make sure to multiply everything through by that number in order for it to get rid of those fractions. Okay? Questions about that one? That's as complicated as it's going to get. I don't know if I've given you anything on a test that's as complicated as this one. Most of them won't be like that first one that we did. All right, let's wrap up with, I think electroplating is our last.
Is that like the peak of complicatedness?
The electroplating? No, we're not actually even going to really do any balance in reactions or anything. I just want you guys to be aware of how electroplating works, and then we're going to do a quick experiment. So yes, thankfully it's not going to really get any harder as far as the redox reactions go. Just as a note, if you look at page 377, you'll see a picture of a zinc carbon battery. And so this is, you can kind of get some insight as to how it's set up on the inside. And you can kind of see the different pieces there that you can map to the galvanic cell that we drew up on the board, right? You can see the cathode and the anode identified, and you can see how they use, how they have there's a carbon cathode in the middle there. There's some powder, MnO2 and powder carbon in one section. There's an NH4Cl paste. And these are what we call dry cells because there's not actually any liquid in it. So in these batteries here, we've got a bunch of dry components, but it's a redox reaction that's happening on the inside to produce the electricity. Do they have a picture of an alkaline battery? An alkaline battery, the reason it's called an alkaline battery is that the salt bridge that's used in an alkaline battery is a base. And so remember, if something is basic versus being acidic, we say that it's alkaline. And so it uses a base for the salt bridge, like for example, potassium hydroxide, and that's why those are called alkaline batteries. And then for automobile batteries, there's no picture of that either. But automobile batteries do have liquid solutions in them, and they're called lead acid batteries and contain a lot of liquid. So just a variety of different kind of batteries, but all of which use these redox reactions to produce electricity. So that's pretty cool. All right, so let's talk about electroplating. Redox reactions can also be used to coat an object with a metal. So when using reduction to coat an object with a metal, we call this electroplating. All right, so I just want you to be aware of what electroplating is, and we're doing an experiment today, so I didn't have nearly as much copper 2 sulfate solution as I thought I had today, so not able to actually have a bunch of groups do it on our own, but I'll give you guys some glasses. Just don't have some. So everybody's got their goggles and in case our in case our battery explodes, right? Gets anything in their eyes. And all we're doing the experiment a little bit differently than it's listed in the book. It's on page 12.3, so I'm going to do a little bit more lecturing, but because we need about 5 minutes for this process to take place. But the way the experiment reads in the book, experiment 12.3 on page 378, is that we're going to take solid copper sulfate, and the first thing we're going to do is we're going to dissolve it in water. All right, so step 1 of your instructions is put a half a teaspoon or 2 large chunks of cupric sulfate in a 250 milliliter beaker that you fill up about 3/4 of the way full, and then you stir it. And they're like, it's okay if it doesn't fully dissolve in there. Just make sure that the solution is noticeably blue. Would you guys say our solution is noticeably blue? Yep. So we've already got a noticeably blue solution. So we've already done step number 1 ahead of time. Step number 1, you create the solution, which we already have. And then, so we're going to go ahead and just pour the rest of this in here. Now, I will tell you, let me have a couple of students verify this. Does the bottom of this battery look nice and silver? No corrosion on it or anything? No discoloration? Looks nice. Can everybody see that? We don't have anything on the bottom. So what we're doing here is we're going to try to coat the bottom of this battery. See, it's nice and silver right now. We're going to try to put, it's not going to be a solid coating, but we're going to try to get some, we've got a solution of copper sulfate, and so we're going to try to plate the bottom of this battery with some solid copper, all right, which is this process of electroplating that we're talking about. So let me show the camera. Is it in the camera there? Let's see. Yeah, can you see that? It really won't. It's kind of weird doing this backwards. Will it focus in on that? There we go. Now there we go. Okay. So there's nothing on the bottom, so we can examine it afterwards and see what happens. Pour this solution on top of this. Make sure the battery's good and covered. Now, like I said in the last class, or I don't know if I said this or not, but I was about to say it. In the last class, we didn't actually, we didn't get a lot of copper on the bottom of the battery. And the battery that I used was a battery that had previously been in a handheld recorder, and so it wasn't fully charged, right? And so I'm using a battery now that's a brand new one. So I'm hoping maybe because this battery's stronger that we'll get more of a reaction and we'll see more electroplating on there. But let's see, we're at 224 now, so we're going to check at about 230 and see if we've got some copper on there. All right. But let me say this about your steps for this lab, and I pointed that out in the last class too. I want to make sure you guys know this because we've occasionally done labs in here and we haven't followed the exact steps that are in the book. All right. So when you write your lab report for the lab that we've done in class, I don't expect to see the steps that are in the book because we didn't do the exact steps that are in the book, right? You're writing a lab report for the lab that you performed. And your lab procedures are a little bit different from what's in the book. Namely, in this one here, we didn't, we do have a 250 milliliter beaker, like they said, but we didn't add, we didn't take a teaspoon of solid copper sulfate and fill up the beaker 2/3 of the way full, right? We just took a copper sulfate solution that we already had and we made sure that we put enough in there to cover our battery. Okay, so that should be the way that your procedures read. Now, if you want to note that this is a little different than the steps that are in the book, and maybe when you talk about experimental error, maybe you want to say, this is potentially the experimental error. We didn't do this exactly like it said, and maybe that's why we didn't get as much copper on the bottom. That's fine. But I expect your steps to match what we actually did, right? I don't want to see that you've just copied down the steps that are in the book. You're supposed to write down the procedure as you did the lab, okay? So we'll give that about 5 minutes to work its magic. But I'm going to write down a chemical equation, which is what we use in gold electroplating. And it looks like this. All right. So this is the reaction that we would use, and I want to just let's analyze its oxidation state, the oxidation states of each of the atoms, just to verify this is indeed a redox reaction. So what's the oxidation state for AU?
0.
0, right? Just a single element all by itself. This is going to help you kind of think back over the 7 steps that we learned last week, right? What about HCl? What's the oxidation state for HCl?
H is 1 plus. And then the Cl be 1 negative, I believe?
It has to be 1 negative, right? So it balances overall. We've got a total of 0 on that. What about here? AuCl2, that's an ionic compound. So remember I told you guys you could, when you recognize it as an ionic compound, you can do the reverse of swap and drop and figure out your charges that way, right? Or you could see that Au is in column 2A in the book, so it's going to have a 2 plus charge, and then Cl is going to have a 1 minus charge. All right? Is that clear to everybody? And then finally H2, homonuclear diatomic, molecules made up of a single element, a single type of atom, or they're always going to have a charge of 0, right?
This is the equation in the book, right?
Uh-huh. Should be. Did I do something wrong?
AuCl3.
AuCl3, okay. Oh, that must mean then that AU is not in column 2A, it must be in column 3A. Where is AU? Or is AU in one of those,
It's in the word.
is it in our weird ones in the middle there?
Yeah.
So yeah, when we got
Yeah, it is. It's in 1B.
1B, okay. Well, thanks for pointing that out, because if that's the case, then we fall back to
Cl should be
that Cl's got to be a what?
1.
It's 1 negative, right?
1 negative.
It's in column 7A. Remember that was down in our steps 6 and 7. When if it doesn't follow any of the other rules, that you drop down to that one. So 1 negative here. So if that's a 1 negative, the total here is going to be 3 negative. So AU has to be 3 plus, right? Good catch on that. So I'm actually that's worth a +2 right there. Nice job. She's like yes. That's an accomplishment. And I also I need to fix my notes. AuCl plus. I got a black pen. That's pretty good. I taught this last year, and I taught it to the class this morning, and nobody's called that. So it's the 3rd time I've called it. Finally, someone noticed the mistake. Nice job. So it is indeed a redox reaction. Which element is oxidized and which one's reduced? Is Cl reduced or oxidized? No, it's the same on both sides, right? So it's got to be Au and H. So Au goes from 0 to 3 plus, so it becomes more positive. It loses electrons, so Au is oxidized. Leo. Right? Loses electrons means that it's oxidized. And then Cl went from 1 negative, H went from 1 plus to 0. So it went down on the number line, it became more negative, so it's reduced. Because GR gains electrons, it got more negative, it gained electrons and was reduced. So it is indeed a redox reaction. And we could also check and make sure that it's balanced. Right? They didn't tell us to do that, but since we were just learning about that, it wouldn't be a bad exercise to just verify this is balanced. And so it turns out here when you combine these together, you get 0. And this is actually, since you've got 6 of each of these, this would be a 6 plus and a 6 negative, but it doesn't matter because they both add up to 0 either way. We got 2 of these and that's still 0. For this one here, since we got a 2 times both of them, we've got 2 times 3 plus is 6 plus, and we've got a total of 3 minus there, 3 negative, and 2 times 3 negative is 6 negative, and then this is 0. So it does everything adds up to be 0 on both sides, so we're balanced electrically as well. Did everybody follow how I did that? Because that's kind of the stuff that, the new stuff we learned today. So again, I want to make sure that you can balance the equation electrically as well as atomically. No questions about that? All right. One thing to note before we check our battery, we're a little bit over, but it doesn't say that we could leave it in there for too long. So I'm going to assume a couple more minutes, not going to matter. There are some negative redox reactions. In other words, redox reactions that we don't tend to do on purpose, right? We consider them to be bad, reactions that aren't useful. And so an example of that would be rust forming. So when rust forms on iron or steel, it's a redox reaction, but rust is a form of term I know you're familiar with, corrosion, all right? Which is the chemical. This is a really weird word for me to spell because I don't pronounce it the way that it's spelled. Deterioration. It should be deterioration, and I don't put that "er" in the middle there typically when I say it. But the chemical deterioration of a substance. And it's usually due to oxidation. All right, let's see if we've got any copper on our battery here. This is the copper top battery. So this one will definitely work, right? So it's already slanted towards copper, so we should be very successful with a Duracell in there. Let's see. That was the glove. It's the glove. Let's see. Do I have it? Yeah. Let you guys quit writing before we check it. Okay, you guys ready? See what we see? All right, you guys tell me. Can you tell?
Yeah, around the outside.
It's on the outside, right?
Uh-huh.
It looks a little, it's almost like corroded looking a little bit on the outside there. We got some in the middle of it last time, but it was just kind of like a thin line. It wasn't very strong.
It's kind of like a layer over it.
Yeah, that's what I was wondering if it's not, because I'm colorblind, maybe it's not standing out to me much.
Yeah, there is actually a layer over the top because it was a lot darker than that. You could barely see it. Mm-hmm.
So let's see if everybody else agrees. Do you agree that overall it looks like we've got some discoloration there? It's not as silver as it was before. Yeah, it definitely looks, like I said, looks kind of dingy, but it's because we've got some copper forming on the plating on the bottom of it there. You guys see that?
So is that like the kind of brownish?
Yeah, right, exactly. Yeah, because it was nice and clean looking before. Like I said, this was a brand new battery, so it almost looks like, if I just looked at it, I'd think this battery's been sitting down for a while, and sitting around for a while, and you'll get that corrosion on the outside of a battery, and you may have heard that referred to as oxidation. Like, have you ever looked up how to clean like a device that's got some corrosion on the inside? You know, if you look up online how to clean the stuff off of there, sometimes when you look it up, you'll come across that word oxidation. And it's talking about this. It's because there was some kind of reaction that caused some other substance to form on there. I guess I could take these off now because we already pulled it out, and I had to. So let's see if we can get that in view on the. Sort of see that around the edge there, and like we said, just kind of overall, it's almost kind of dirty looking, like there's a thin film of something over it. So it would have been really cool if we pulled it out and it looked exactly like the stuff around the top, right? That would have been kind of neat. It's not that dramatic. But it only happens on the bottom part. It only happens on that, which is the negative side. Right. Just like we saw, well, let's see, the negative side in our galvanic cell was the left side, right? Yeah, because the electrons are flowing to the positive side. But what's it's kind of like what's happening here as the gold, where the oxidation takes place, right? It's losing the electrons, and so that plating, this solid gold, is happening as that process takes place. It is forming on the metal. On the what's that side? The negative side there, is that the cathode or the anode? The
Anode.
Yeah.
Negative side's anode.
The negative side is the anode side, and so it was forming on the. Let me make sure verify that's what he said in the book, that it forms on the anode of the battery. So only on that bottom part there. All right. Well, that's it for today. Oh, that's it for today.